Alrighty, so here's the problem. This is consider 3 voltaic cells, each similar to the one shown in figure 20.5. In each voltaic cell, one half cell contains a 1.0 molar iron nitrate aqueous solution with an iron electrode. Contents of the overall half cells are as follows. In cell 1, we have a 1 molar copper chloride solution with a copper electrode. In cell 2, we have a 1 molar nickel chloride solution with a nickel electrode. Cell 3, a 1 molar zinc chloride solution with a zinc electrode. In which voltaic cells does iron act as the anode? So you have 3 different ones. And, all right, so if we look, I'll just draw them out, right? We have, in one container here, container 1, we have copper, right? Copper electrode, and we have copper 2+ ions floating in solution. Second one, nickel. We have nickel 2+ ions in solution. And the last one, right, is the zinc. And zinc 2+ ions in solution. All right, and we're trying to figure out we have an iron, right? Iron electrode here. And we're trying to figure out which of these, right, when they're connected, whether that one or that one or that one, when they're connected, where the iron is going to act as the anode. Right, so when these are going to obviously need to act as the cathode. So if you recall, right, if the anode, that means this is going to be related to the oil side, right? And then these are going to be the rig side, right? These are going to be the cathodes. All right. So we need to figure out which is this. So we need to, in order to do this, we need to use the table and figure out, the difference, because if you recall, let me see if I don't have a picture anywhere in here, do I? No. See if I can find the picture I'm looking for. There it is, right here. I'm just going to make a quick swap. All right, there we go. All right, so just for a quick swap, right, you can see here in this picture, right, your anode is the one that's going to be giving up the 2 electrons, and it's going to be the one that's more negative, and it's going to be sending electrons down to the cathode, which is the one that's going to be gaining the electrons, because it's a reduction. Reduction is gain, right? So it's going to be the more positive number. That makes sense so far? So if we go back to the problem, so wouldn't gaining electrons make it more negative? When we're talking about, so this table here is what we're looking at. So the table down below, which is kind of tiny. Let me see if I can blow this up. Right. When we're talking about substances that are more negative, all we're talking about, Freddie, here is the comparison to the standard reduction potentials when we're comparing it to hydrogen. So something that's more negative means that it's going to have a less favorable ability to gain electrons. So if we look at the very top, right, fluorine has a very large positive number. It means it's a very favorable reaction. A reduction is very favorable for fluorine. And as you move down the table, as your number gets more and more negative, right, as you're, just moving from the first line to the second line, you're getting more negative, even though it's still a positive number. But as you're moving down, the reduction reaction ends up less favorable. So the more negative the number only refers to, it doesn't have anything to do with the gaining of electrons per se. So, not what the final product is. It has to do with a favorable or unfavorable process. Does that answer your question? Hopefully. But anyway, if not, ask a different way. All right. So we go back to the problem up above. That means we need to look for substances, in comparison to iron, and look for those substances and try to determine which of these three solution mixtures, cell 1, cell 2, or cell 3, is going to be favorable with iron as an electrode. So if we go back down here, I'm having a hard time here trying to pinch. So we can look at the table. Right, we have the iron reaction. Let's see if I can find it. All right, so we have iron. Let me change the color here. All right, so we have iron right there. All right, so if we have iron and we want to compare that to zinc. Right. There's another iron here. Oh, don't forget about that iron. And then we also have, well, actually, this is not iron. Let me erase my earlier comment. This is not forming iron electrode. This is iron 2+. We want the actual iron one, which is down below. So my bad. I didn't read it as closely as I should have. So we're talking about, we want specifically iron. We have zinc. What were the other two? Drawing a blank. Copper and nickel. All right. So we have the copper reaction right here. Oops. All right. There's copper and the nickel. So you can see, if simple analysis, we don't have to go through all the calculations of calculating. You could go through and you could calculate the E of the cell and do all the calculations, or you can just notice that, okay, only the copper and the nickel are going to be have a higher standard reduction potential, so they would prefer to be reduced than the iron, so they're going to be the cathode, whereas the zinc in this case is not. So if you see, if we go back to the problem, let me shrink this back down again. Right, so in this case, we determined that essentially the zinc solution here is not going to be favorable, so it's only going to be cells 1 and 2. That makes sense, Sophia? Annie wanted on problem set 19. These are in-class problems, I assume, Annie? Or did you want others? Part D. You talking about this one right here? Oh, and the homework. That's right. So you want homework assignments. Part D. All right. Says the amount of work that a system can do on its surroundings depend on the path of the process. So when we're talking about, so this one just basically gives you the answer, right? It says, yes, the reversible pathway can accomplish the maximum amount of work on its surroundings because no entropy is lost to the universe. If you think about, I don't have the other questions here. Where we talk about path versus state functions, path functions versus state functions. Right? When we talk about work, and I'm trying to see, let me see if I have the slide handy. Trying to find it, but I can't seem to find it. I can't find what I'm looking for. We have, path functions and state functions. So if we're thinking about this one for part D, right, we have entropy, right? We talked about entropy, and in particular, that entropy, right, this was a, see, right, this was a state function, right? And this only has to do because, we have our initial minus our final, and we talked about enthalpy, right? State function as well, right? We have our initial minus our final and how we got there in between. But if you think about work, right, and the ability of something to do work, and I'm trying to recall where in the chapter this showed up. Right. If you think about it from the common sense perspective, right, the path that you take to do work is very much dependent, going to determine, the work is definitely dependent on the path that you take to get to the end, right? If somebody's using a jackhammer to break a rock versus a pickaxe, the path to get there is going to require different amounts of work. I'm just trying to see if I can find the particular section to point you to. This is stuff that we talked about way back when. Back in chapter 6, and was one of the areas where we talked about it in regards to quantization and path, but that's not the one I wanted. Pressure volume work 172. It's probably around 168 in the textbook. It's approximately when they start talking about it. It's in chapter 5 when we're talking about thermal chemistry and heat. They talk about work that can be done and the relationship of delta E to heat and work. And there was a couple graphs. I'm trying to see if I can find the exact thing I'm talking about. That it was a state function. I'm not finding the answer I'm looking for, unfortunately. Let me try to think about this from a path versus a state function. If you think about the think about it this way. You have a chemical reaction, right? You start at a certain point and you increase in energy and you come down to the bottom. And if you think about from a delta H perspective, right, the delta H is just beginning to end, right? The enthalpy component. If we have a reaction, another reaction sitting right here, right? And we start at the same point, our activation energy is much smaller, but we drop down to the same energy. We get the same exact delta H, right? So these two delta H's are exactly equal to one another. The enthalpy of that reaction is the same. The path that we did, right, for the amount of work. So you think about the heat that's given off during this reaction. The heat that's given off this reaction that can be productive, right? Because if we think about our delta E is equal to Q plus W, right? So the work that we can get out of the system is related to the heat of the system. And remember, we talked about how heat was related to entropy and the energy, overall energy of the system. And this enthalpy is also related to Q as well. But anyway, we can see how the overall energy in the system is going to be dependent on the work that we can get out of it is going to be dependent on the path that we get through to here. And this path is going to directly affect the amount of work that we can get out, right? The path has to do with the amount of delta E that we're giving, we're requiring. The amount of energy that we need to put into the system, the activation energy, so to speak, is going to be different, but the work that we can get out in the end is going to be the same. And it all depends on the path, right? We're going uphill and back downhill versus a smaller hill. Or let's say you could have another one where you had an intermediate and worked your way through. the path is very important when we're talking about work. If all you did was lift something up away from gravity and then drop it back down, then, for example, something like that wouldn't take work into account as a path function. It would just be a state function because you're just going up against gravity and then dropping it back down. But as soon as you get anything that's not a single trajectory, then you're going to have, such as a chemical reaction, you're not going to have work is going to be a path function. Right, and the other one was number 2. Which one in number 2? Just any particular one? B. Without further information, can you conclude that the amount of heat transferred to the system as it goes from state 1 to state 2 is the same or different as compared to that going from state 2 to back to state 1? Okay, this is all right. Oh. Yeah, so the answer is no, because you don't have enough information. So you don't have the Q and W. You don't know anything about the path. Sorry. It's meant to make you think about all these things in depth. All right, Sophia, I think you had another question. You don't like thinking. Go back to living on a farm. Wake up, milk your goats. Have you been milking your goats since you've been back home? You need to do them now. Is this chapter 20 in-class problem, Sophia? The 7th one, or is it homework? Homework. All right. Number 7 says, given the following half reactions and associated standard reduction potentials, where you have this gold bromide, tetrabromide, anion, plus 3 electrons goes to gold as a solid, plus 4 bromides, and you have a standard reduction potential of negative 0.86. Then you have europium plus an electron going to europium 3 plus an electron going to europium 2 plus with a standard reduction potential of 0.43. And then the periodate going plus water plus 2 electrons going to iodine plus hydroxide. Standard reduction potential of 0.49. It says write the equation for the combination of these half cell reactions that leads to the largest positive EMF and calculate the value. Well, for this, in order to do this, you would need to think in terms of, if you want the largest EMF, right, because you have your delta E of the cell, right, is the delta, what is the delta E reduction of the anode? So mark my words, minus delta E reduction of the cathode. Right? So in these terms, you want in order to get the largest difference, you need the largest positive right here and the largest negative. Here, right? So you need largest positive, largest negative. So in order to do that, you can see that you're going to need to take the last equation and the first equation. And when you take the last equation and the first equation, and you've essentially react them together, which is, what are they doing here? The first step. I don't know why the answer is written this way. I think there's something missing here. There should be this equation should be up here when you add them together first. So this looks like something got cut off at the top of the answer key here. This is cut and paste, my apology. This is just a problem right out of the back of the textbook, and I cut and paste the answers right out of the back of the textbook. And it looks like this section, so this equation right here should be here, and it needed to be, then you add, multiply to balance them to get the, balanced overall equation here. And so to write the equation, so let me just write that over here. So we have our AU Br4 minus plus 3 electrons going to gold plus 4 Br minus. Right, and then we have in the last equation actually, before I do that, I need to, well, I'll redo something in a second. This is going to I minus plus 2 hydroxide. So if you're copying, don't write exactly what I've written down yet. I just realized I made a mistake. So we needed to first recognize that both of these electrons are on the same side, right? So in order to determine which is reduced and which is oxidized, right, the anode, the one with the largest reduction potential is going to be the one that's doing the, that's going to be reduced. So this equation is going to stay in the forward direction. The upper equation, because it's the smallest number, is going to go in the reverse direction, which is what I should have done here. So let me reverse the equation. So you get to see what mistakes happen. So you actually have gold plus 4 Br minus going to AU Br4 minus plus 3 electrons. So you have to invert the equation in the opposite direction, because since it's at the cathode, it's going to be going in the opposite direction, right? It's being, did I have this equation right? Give me 1 second. I want to make sure I'm not entering this equation. Yes, that's my problem. I wrote it incorrectly here. So it's a good thing I give you the equations. I realized I just did this. It's supposed to be cathode in the beginning and anode afterwards. Cathode, anode. All right. My bad. I'm sorry. So you have your cathode and your anode. So your cathode is going to be the one that's being reduced, and you're going to be subtracting from that the anode, which is going to be the smallest or the most negative number. So we need to balance these equations. So you can see you're going to need to multiply the first equation by 2, and the second equation needs to be multiplied by 3, right, in order to have 6 electrons in both cases. And after you do that, you can see that what you end up with is 2 gold plus 8 bromide plus the 3 IO, right? So you're distributing, you have 2 gold plus 8 bromide plus 3 IO minus plus 3 water molecules. You're distributing here. You would have 6 electrons, but those are going to cancel on both sides, and then you distribute, right? You have your 2 gold bromide plus your 3 iodides plus your 6 hydroxides. And then you can calculate the EMF by just simply doing the math there. Does that make more sense now? You have 10 and V. Well, they shouldn't have tin and V. Wow. Why is it? That's what I get for just copying and pasting answers out of the back of the, the answer key. That's not correct at all. So, Sophia, this goes to show you, this is the same answer key as last semester, and you're the first person that's brought this to my attention. So, either nobody understood it when they looked at it, or they just didn't care. I didn't bring it to my attention. So, so if we look at what's going on here, so we have to do obviously, to do the smallest, we have to figure out which is the smallest gap. So you can see the smallest gap is going to be the one between let me just change color my pens. Right, but the one between the first 2 equations is going to be the smallest gap. That makes sense. So you have the europium and the gold equations. So this equation here would not be correct, right? So we would have our forward reaction is going to now be the europium run, right? So we have our EU 3 plus an electron going to EU 2 plus. And then we have in the second equation, gold plus 4 bromide going to EU Br 4 minus plus 3 electrons. And we have to balance this. So this is going to just be simply multiplied by 1, so there's no change there, right? Whereas we're going to multiply the first equation by 3. So then when we add these up, so we end up with 3 EU 3 plus gold plus 4 bromide goes to 3 EU 2 plus AU Br 4 minus. And I've canceled the electrons from both sides. And then you can do the math here. So this is going to be actually, did I just do the, yeah, so it should be minus 0.86, so we're going to have, I didn't even do the math right here. Okay, so then you're going to have minus 0.43 minus a negative 0.86, which gives you your E naught of 0.43 volts. You say let you drop an exam as punishment, Annie? You don't need to drop anything. Dropping exams is just a way to let faculty members think you feel but good about yourself. But in the end, if everybody drops their lowest exam, it does nothing to the average of the class. All it does is, change the scale. I'm a purist, if you haven't noticed. You get the grades, and then I'll scale in the end. You'll be good. Other questions? Makes more sense now. Sorry, Sophia. I'll have to change this answer key because this answer key is pretty messed up. Yes, ready. Chapter 19, problem 5. Restore you. Computer just froze. I think I'm asking too much for. Let me trying to bring something up. Give me 1 second. Let me go here, Freddie. This will hopefully answer your question. If my computer doesn't freeze up completely. Strange. My computer just went haywire. I just lost it all. Oh, there we go. All right. So when we're talking about the reverse for these particular for this particular type of problem, Freddie, we're talking about this part of the problem here. Let me see if I can blow this up to full screen. Of course, I'm not going to be able to, so I won't be able to write on it. So when we're talking about here, my computer's going really slow right now, so I can't click on anything. The Q reverse is, we're talking about the heat that's, you see the last statement there, Q reverse is the heat that would be transferred if the process were reversible. So what we're talking about is the heat that's being transferred from the surroundings at a given temperature. So, if you, I wish I could write on this right now. So the fact that the reverse is just the reverse of the direction that the system would be working. Typically the system would be transferring energy to the surroundings. And what we're doing with Q reverse is we're measuring the potential, that the heat that would be transferred back from the surroundings to the system. And that's all the reverse means. And the numbers, whether you actually have a negative number or a positive number, has to do with the delta H of fusion and which direction you're actually going. So it could be a negative number or it could be a positive number, but it depends independently on the delta H of fusion and which direction you're actually going, if that makes sense. All right, let me just, so in this particular problem, because the entropy change is based on the vaporization of water, right? The vaporization system is, path where your entropy is increasing, right? Because you're going from a liquid to a vapor. So you would expect to have an overall delta S with a positive number, right? Because you have your enthalpy of that particular reaction is going to be, if you're your enthalpy is going to be going, and the enthalpy in the opposite direction, or the heat delta H of fusion in the opposite direction, right, is going to be going from a vapor to a liquid, which would be a positive number, right? Because obviously if you're heating a system up, you'd get a more negative number, but since the negative or the reverse of that is going to be a positive number. It's very convoluted explanation, but that's basically what's going on. All right, other questions? Number 2, part C, same problem set, 20. All right, is it right here, isn't it? Yes. All right. So this problem says indicate whether the following balanced equations involve oxidation reduction. If they do, identify the elements that undergo changes in oxidation number. Identify the oxidation numbers for all the elements and the reactants and products, and state the total number of electrons transferred in each reaction. All right. So we have part C here. So we have our H2SO4 reacting with sodium bromide to form bromine, sulfur dioxide, and sodium sulfate and water. All right. So we have to go through and figure out which substances are, one of the easiest things when you're working through this is first determine which substances don't change. That would be my first suggestion. Which substances don't change? So we can see that the sodium ion, it's a spectator, right? It stays as a sodium ion in both cases, right? The protons, right? Remember, this exists as an H. It's also over in water over here. So at least in terms of oxidation numbers, so the protons aren't changing here, or, right? So we have the associated. Let me go changes. So the sodium is up because it's an ion. It's always in group 1. It's going to be sodium plus. Protons are +1. Yes, hydrogen can either be the hydrogen +1, hydrogen 0 as H2, or it can be H- when it's coupled with a metal. So it has to be H+ here. And we can say, okay, now the last things that we need to look at are our other molecules. We have SO4 going to SO2, right? So the sulfur atom, let me just draw it out here. We think SO4, right? We have each oxygen is worth a 2 minus, right? We have 4 of them, right? And if we think about, we have, for the whole molecule, we have 2 H pluses. Let me try to draw this differently. So if we have, let me draw them up here. We have 2 H pluses, right? So that means that this has to have an overall 2 minus charge on the sulfate ion. So that this, and for this sulfur to balance all of this out, and I guess I could probably have kept this all together. Let me do that this way. Let me just keep it all together and make more sense. H2SO4. So each of these are going to be worth 2 plus from the 2 protons. This is going to be worth -8 for our oxygens. So the sulfur has to be worth a 6 plus overall here. And then we look at our SO2, right? So we have 2 negatives times 2, which is overall -4. So this sulfur has to be a +4, right? So our sulfur is going from +6 to +4. And then we have our bromine, right? In terms of sodium bromide, NaBr. So if sodium is +1, bromide has to be -1. And we know that bromides are -1 because they're halogens. And then that's going over to Br2, right? So Br2 is in its elemental form, so this is going to be 0. So we're going from -1 to 0 for bromine. And did we cover anything else? It's the standard periodic table. I don't think it has charges on it any. You have to understand how to do charges still. Sorry. It's one of those important things you need to know for the rest of your chemical life. Some of these you'll eventually just be memorized. All right, so did I answer that? Sulfur is reduced, right? So this is from a +6 to a +4. That's a reduction process, right? Because we're gaining electrons, right? So we're adding 2 electrons here. And obviously going from bromide, right? We have 2 sodium bromides here that need to go forward, right? We're going to be losing 2 electrons in the overall process here. So that's going to be our oxidation event. And we have a total of 2 electrons being transferred. Does that answer your question? So bromine is actually only losing, each bromine is losing 1, right? So you have 1 bromine as a -1 plus another bromine as a -1. And the combination of both of those gives us Br2 plus 2 electrons. So each one of these, so from this bromine goes to become a Br0, and this one becomes a Br0. But Br0 exists as a diatomic molecule. So each one of these loses 1 electron in the process. So you lose an overall two electrons. All right, Freddie, good luck. See you later. To answer your question, Sophia, how does this compare with B? For B here, we have lead oxide. So you can see we have, oops, over here, we have PbO2. So all oxygen we always know is a 2 minus, right? We have 2 of them, times 2, right? So there's an overall 4- charge here. So this lead has to be a +4 beforehand. Then we have our lead here. I'm going to draw the whole thing out. I know you're just asking about oxygen, but I'm going to draw the whole thing for others who might want to know. Right, so we have, this is going to be a 2-, so this lead is now going to be a 2+ charge. So you can see that the lead is going from a 4+ to a 2+. And there are obviously, right, we have 2 of these, just like we have 2 of these. So overall, we see a transfer occurring, between, each of these. So we're going from a 4+ to a 2+, and we have, so the overall, if we look at what's going on with lead, we have lead as a PB is a 4+. We have 2 of them, and this is going to be, in order to go to a 2+, we have to gain, 4 electrons, right, to go over to make 2 lead as a 2+, right? Because overall on this side, we have an overall 8+ charge here, and we have an overall 4+ charge there. So we need to gain, to balance both sides, we need to gain 4 electrons. If we look at the oxygen atoms, I'll draw them up above, right? So our oxygen, initially we have, let me change the color of my pen for a second. We initially have 2 oxygens times 2, right, that are in the 2- state. Afterwards, right, I probably shouldn't have done that. We still have 2 oxygens, right, in the product that are in the 2- state, right? 2 of them are still in the 2- state. Right, so we have a total of 4 oxygens beforehand that are in the 2- state, right? Because we have both of these, there are 4 oxygens that are in the 2- state. Afterwards, we still have two that are left in the 2- state, as you can see here, right? These 2 are still left in the 2- state. But that means 2 of our oxygens then are converted to O2, right? So we have an oxygen 2- plus another oxygen with a 2- charge going to O2. And you can see that we're basically going from the 2- state to the oxygen in the 0 state. So each of these oxygens has to release 4 electrons. I mean, a total of 2 electrons each, which gives us 4 electrons out in the product. Right, because this oxygen is going to the oxygen in the 0 state, and this one is also going to oxygen in the 0 state. And in the process, they lose 2 electrons. Make sense? So the oxygen atom is then the thing that's being, right, it's being reduced. All right, other questions? Homework part C, 6C. So you want to predict, and this one for the following pairs, predict which substances possess the larger entropy per mole. Right, so we have, in the first example, in part C, we have half a mole of N2 gas at 298 Kelvin with a 20-liter volume. where we have half a mole of methane gas at 298 K, 20 liter volume. So we have identical temperatures, so temperatures aren't going to affect this. We have identical volumes, so the volumes aren't going to affect us. All we have to think about now is the difference in the compounds, because the number of moles that we have is exactly the same. So all we have to do is compare N2 versus CH4. Now, if you're thinking about the these two compounds, you have nitrogen, exists like this, and we have methane. Right. Now we have our ability for our molecules to rotate, they can bend, they can stretch. Right? There's all different things that these molecules can do. We look at nitrogen, it can, it has the ability to stretch, right? It can stretch outwards and collapse coming back inwards. Rotation, there's maybe one rotation where if it maybe a pinwheel fashion where it could rotate, but if it's rotating down the axis, you really don't get a lot. There's no bending that can occur, right? Because there's just one bond. It's a triple bond. So you have limited movements, whereas if you look at methane, right, each of these bonds can stretch or can compress. The molecule, we can have bending action occurring in between each of these bonds. We can have the molecule rotate. It's spherical, so rotation, there won't be really very much for rotation. Rotation, as a tetrahedral molecule, methane shouldn't do much for rotating, but we have a lot more combinations of movements, right? We could have bending and stretching happening in the molecule at the same time. So it's the more complex, the more bonds that you have, the more movements you have in the combination, which leads to the higher degrees of freedom or the overall higher entropy, because you have more possible microstates, right? Those microstates W that exist, we have more possible microstates with methane than we do with nitrogen gas. Does that make sense? Because you have a lot more movements. Yeah, molar mass alone wouldn't do it. Well, you are correct though, right? The molar mass of this would be 28 for nitrogen and 12, 14, 16, right, versus 16. So on a pure molar mass basis, you're correct. So the molar mass does have some part to do with it, but it's the more complexity is the thing that leads to a lot more microstates that are possible, which is a lot more entropy. It overcomes the molar mass to some extent. That. More questions? Well, they put up the reference sheet. I guess sometime tomorrow. I'm in the process of writing the exam. I'm not quite halfway through yet. So I'm still writing the exam. And I usually try to put it together. Is the exam long? It's going to be like usual. Might be a few extra questions, so trying to put a few more. These two chapters have a lot more conceptual matter in addition to mathematical concepts. So there are a lot of concepts in here that can be tested with some simple questions, which won't require as much calculation. So they'll be faster. So you might have a few more, quicker questions that you can answer in addition to some of the math ones. Plus it is, You've got plenty of time. You're supposed to be scheduled for 3 hours. Any more questions? It's kind of sad. Everybody's done after this. I don't get to say goodbye. Everybody's just poof, disappears. As the country's starting to open up, don't waste your summer. If you have the opportunity, still do an internship or something. Just wear a face mask. As opposed to getting a job. You know, if you were planning on hunkering down and hiding in your house, that's fine too. Everywhere but Massachusetts. Yeah, Massachusetts isn't looking too good right now. The Northeast in general, I don't know if I would. Yeah. You take a chance no matter what. Every day you walk out your door, you take some chances. I'm hoping that they'll have a treatment soon. They're getting some promising results, right? No more questions? Everybody's good? Everybody's got this? If you showed up late, I recorded the session, so Elizabeth. Oh, we already lost some other people. So if you missed any of the first questions, they're still there. All right, see you later, everyone.